Hello everyone, my name is Neha Prakash Karyapanavar from BSc Second Sem student PCM combination Sri Siddheshwara Government First Grade College Nargun. Today I will discussing about molecular orbital treatment of homonuclear diatomic molecule O2 and calculate the relationship between bond length, bond order, bond energy and magnetic properties. Next, I will move to the introduction. In 1932, the chemist Hugh Mulliken and others proposed a new theory known as molecular orbital theory. In shortcut, we can say MOT. And later, this theory was developed by Leonard Jones and Charles Coulson. Okay, next point is molecular orbital theory. According to molecular orbital theory, the atomic orbitals of the bonded atoms lost their identity. They mix up to form the molecular orbitals. Molecular is regarded as polynuclear structure. The space around the nuclei is distributed into molecular orbitals. Next, molecular orbital treatment of homonuclear diatomic molecule O2. Using our knowledge of how the different types of atomic orbitals can overlap and form molecular orbitals, we can now construct molecular orbital diagrams for simple diatomic molecules. In these cases, we can draw, visualize, and possible ways the valence atomic orbitals on both atoms can overlap. Next, I will move to the creating molecular orbital diagrams. In this, we can draw the diagram regarded some points. Those are first point, include all the valence atomic orbitals on both atoms whether they are empty or filled. Next point, the total number of atomic orbitals must always equal the total number of molecular orbitals. Next point, bonding molecular orbitals are more stable than the atomic orbitals and increase the electron density between the nuclei. Next point, anti-bonding molecular orbitals are less stable than the atomic orbitals or decreases the electron density between the nuclei. Then last point, fill the complete diagram with electrons according to the above principle. Next, molecular orbital energy level diagram of O2 molecule. This is the energy level diagram of O2 molecule. In this diagram, the electrons are filled according to the above principle. Next, I will move to the oxygen molecule O2. 8O means 8 oxygen atom, 1s2, 2s2, 2px2, py1, 2pz1. Each oxygen atom has 8 electrons, therefore there are 16 electrons in oxygen molecule. Due to the combination of atomic orbitals of the two oxygen atoms, 10 molecular orbitals are formed. These are filled in the increasing order of their energies. The electronic configuration of O2 is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 is equals to pi 2py2, pi star 2px2 is equals to pi star 2py1. This is the electronic configuration of the O2 molecule. Some explanation regarding the molecule electronic configuration, that is, last two molecular orbitals are half filled due to the Hund's rule. From the above configuration, we have Nb is equals to 10 and Na is equals to 6. Therefore, bond order, the formula of the bond order is half Nb minus Na is equals to half Nb equal to 10 and Na is equals to 6. 10 minus 6 is equals to 2. Next, Hence, there is a double bond in oxygen molecule due to the presence of two unpaired electrons. It is paramagnetic molecular orbital diagram of O2. Bond dissociation energy of O2 molecule is 490 kilojoule per mole and O double bond O bond length is 121 pm. The bond length of O double bond O is 121 pm. Next, I will move to the next concept. Calculate and relationship between the bond length, bond order, bond energy, and magnetic properties. Next, I will move the first bond order. The number of electrons belonging to two atoms are counted and then field energy level diagram. The numbers of electrons occupying in bonding molecular orbitals and antibonding molecular orbitals are counted separately, from which bond order can be defined as one half of the difference between the number of electrons in bonding molecular orbitals and those in the antibonding orbitals. It is also referred as the number of covalent bonds presenting between two atoms in molecule. Next, if number of electrons in the BMOS means bonding molecular orbitals is Nb and those in the ABMOS means anti-bonding molecular orbitals is N2, then bond order, the formula of the bond order is Nb minus Na divided by 2. Bond order may be a whole number, fractional, or even a zero. It may also be positive or negative. Bond order 1, 2 or 3 corresponds to single, double, and triple bond respectively. Next point, bond length. Bond order is inversely proportional to the bond length. Hence, higher the bond order, shorter is the bond length. Next, I will move to the bond dissociation energy. Bond dissociation energy of a molecule is directly proportional to its bond order. Therefore, higher the value of bond order, greater is the bond dissociation energy of the molecule. Next point, and this is the last point, magnetic properties. The magnetic properties of a substance can be determined by examining its electron configuration. It has unpaired electrons, then the substance is paramagnetic, and if all electrons are paired, the substance is the diamagnetic. Next point, molecular orbital theory helps determine both bond order and magnetic properties. I will refer the chemistry book to and Dr. Vinayak M. Nayak, Professor of Fragasam A, and Dr. Kalpana Karwadikar and Dr. Preeti N. Talur. Thank you, one and all.